Welcome to the second lecture of this week in EE557. In the last lecture, we have seen how to calculate the posterior distributions recursively for a stochastic dynamic system. We have seen an infinite dimensional algorithm in general, and in the second lecture, we are going to try to specify that theory for the finite state Markov chains, where we can do our calculations exactly and with finite storage. Let me first review our Bayesian recursion. So we have P0 given minus 1. This is my initial predictive distribution, and that is going to be equal to P of x0. This is the initialization of our Bayesian recursion. And then we have a measurement update. And this measurement update can be written as Pk given k minus 1, k starting from, k given k is, this is a density of xk, then this is equal to, I would have pyk given xk, pk given k minus 1 of xk, divided by the normalization of this numerator. Okay? This is how new information is incorporated in the density domain, new information in yk. Okay? And we have the prediction update to calculate, to complete the recursion. So we have a pk plus 1 given k of xk plus 1. In this case, this is just an integral. So I have pxk plus 1 given xk, and I have uk, and pk given k, xk, and dxk. Okay? This is the so-called Bayesian recursion. So we start with k equals to 0, and we set pk given k minus 1 to the initial state distribution, and then we start from k equals to 0, and we calculate p0 given 0, and then p1 given 0, and then p1 given 1, p2 given 1, etc. Okay? So now let us concentrate ourselves to the finite state Markov chains. Well, in this case, we know that our state takes finitely many number of elements. It is 1, 2, it can be going until I. Okay, I is an arbitrary, non-zero, positive integer. Okay, and we know that in this case the distributions are horizontal vectrs. This is the initial distribution, so it is P01, P02, going until P0I. Remember, Mubejology actually defined this with pi 0. But I want to continue using p's here instead. So this is a horizontal vector with I elements, and each of these elements are p0i are defined as probability of x0 is equal to I. Okay? This is true for I from 1 to capital I. All right? And actually, we are going to see that these posterior distributions, in the case of a finite state Markov chain, they will be also horizontal vectors like this. Okay? And each of the elements of these horizontal vectors will keep the posterior probabilities of xk being equal to I, given all of the measurements, all of the given information. All right? So in order to be able to define the Markov chain, we are also going to have a transition probability matrix. This transition probability matrix is formed of elements Pij of u. We can have an input in the system, and this Pij of u, they are defined as probability xk plus 1 is equal to j, given xk is equal to I, and uk is equal to u. Okay? That is the definition of the transition probability matrix. And here, ij, they are changing between 1 and I. So here, look at this transition distribution. So pxk plus 1 given xk uk. In the case of finite state Markov chains, this transition distribution is just going to be the transition elements of the transition probability matrix. Okay? This is going to be a horizontal vector. This is going to be a matrix. And that is going to give a matrix vector multiplication, as we did in the past. So then come to the case of partial information in this case. So we assume that we are not able to measure the state in this case exactly. Okay, so we are not defining yk is equal to xk in this case. Instead, yk is going to be another random variable than xk. Let us write measurements. There are two possibilities, of course. In the Markov chains, the finite state Markov chain, the state is a discrete random variable, but the output really does not have to be a discrete random variable. It can be a continuous random variable. So there are two cases. The output variable can be, again, a finite state discrete random variable, or it can be a continuous random variable. Okay? So in this case, the case 1 is yk has finite number of values. In this case, we can say that yk is going to take its values in a set 1, 2, going until capital M. This M does not really have to be equal to the number of states in the Markov chain. So I can have a two-state Markov chain with 3 different values of outputs. Okay? And at each state, the output can take three different values with some probability, of course. So in this case, so I really do not have to show the discrete random variable values with numbers like this. Well, I can just write here xk can take values a, b, c, etc. Finitely many elements. Okay? So sometimes, especially in the example that I'm going to solve, I will show the possible output values using letters like this so that I can differentiate between the values of the state and the values of the output. In this case, what do we have to know to calculate the posterior distribution of state? Of course, we need to define the likelihood function. Okay? In this case, the output is a discrete random variable and the input is a discrete random variable. That means that the output likelihood is going to be a form of probability. So I have yk is equal to, let me say, m, given xk is equal to I. I have to know such probabilities for I from 1 to capital I and m from 1 to capital M. Okay? We need to know these probabilities for all possible values of m and I. So these are the probability that the output takes the value m given that the state is at the ith state. Okay? So here I have the Markov chain states here. So I have 1, 2 going until I, okay? And this part shows xk, and I have the outputs yk. They can take values 1, 2 going until capital M, okay? And at each state, the output can take one of these values. These are not transitions anymore, okay? So the transitions are between states and they are related to this state model. This is showing the output probabilities, all right? And here at state 1, the output can take the can take the value 1 with, let us say, 0.1 probability. Let us say it can take the value 2 with 0.3 probability, and etc. Okay? I have to know all of these probabilities. These probabilities are probability that yk is equal to 1 given xk is equal to 1. Yk is equal to 2 given xk is equal to 1. Yk is equal to m given xk is equal to 1. Okay? And here, the output, the number of state variables of the number of values of the state does not have to be equal to the number of values of the outputs here. So let me give you an example. So this is a two-state Markov chain, and let me say that the output can take 3 values. So I have yk and xk here. All right? Then let us say that these are the probabilities when of the output taking the values 1, 2, 3 when state is equal to 1, and these are the probabilities that the output is going to take the values 1, 2, 3 when the state is 2. I need to know all of these probabilities in order to be able to have the measurement model of the Markov chain. So here I will just show them with different colors. Okay? Let us first look at the probabilities. I'm making this example up. It is not in the notes. Let us say that this probability is 0.1. So when the state is at the first state, the output takes the value 1 with probability 0.1. Let us say this is 0.3. The output takes the value 2 when the state is equal to 1 with probability 0.3. Then what can you say about the probability that the output is going to take the value 3 when the state is equal to 1? Obviously, at any state, the output should take one of these values. Okay? Therefore, the sum of these probabilities should be equal to 1. Okay? So sum of these two are 0.4, so this one should be 0.6. Okay? So here, when you have these probabilities, you need to have the summation m from 1 to capital M, probability that yk is equal to small m, xk is equal to I should be equal to 1. This is true for all I. Okay? Why is that? Because this is a probability distribution. The given condition, given any condition, this is a probability distribution with respect to the discrete variable yk. So it has to sum to 1 with respect to its argument. Okay? So if I sum with respect to the values of m, then I need to get 1 here. The reverse, the other summation is not, does not have to be equal to 1. Okay? So if I fix m, if I sum with respect to different i's, that sum does not have to be equal to 1. Okay? So summation with respect to the argument of the distribution should be equal to 1, not with respect to the given condition. All right? And I can write the other probabilities. When state is equal to 2, the output distribution can be different. Okay? So let me say that in this case, when state is equal to 2, I have the first step, the measurement takes the value 1 with 0.5 probability. Okay? Let us say these two are equal or likely, 0.25. 0.25. Okay? So in this case, as you see, when you look at such a Markov chain, when you measure the output, suppose that output at time k equals to 10 is equal to 2. In that case, you don't know what the current state can be. Okay? So in that case, we really do not know what the state is, whether the state is 1 or 2. The only thing that I can do here is to estimate the probability that the state is equal to 1 or the probability that the state is equal to 2. These two probabilities should sum to 1, and they are the posterior probabilities given the measurement 2. Okay, yk is equal to 2. That is what we would like to do, here. So here I have, this was case 1 when the output is a discrete random variable with finitely many number of values. And let us go to case 2. In this case, the output yk can have infinitely many values, uncountably infinite many values. So yk has uncountably infinite number of values. Okay? In this case, this yk can be an element of Rm. All right? And in this case, the likelihood is not in the form of a probability, of course. It is going to be a density function. Okay? Density function for yk given the value of the state xk is equal to I, and this is going to be the form of the likelihood. Okay? And you have to know these densities with respect to y given all of the states I from 1 to capital I. In that case, you need to know the likelihood in that form. So here let us look at an example. Actually, I have already exemplified. Here, I have already exemplified the discrete random output case. Okay, when I have this, then I need to know all of these values. But you see that because I have a constraint like this, then it is sufficient that I know only the 2 of these values. If I know 0.1 and 0.3, I can actually know that the next one is going to be 0.6. And if I know 0.25 and 0.25 here, I know that the next value is going to be 0.5. But you have to be careful here. The summation with respect to the different measurements, it should be equal to 1, but the summation with respect to different states does not have to be equal to 1. So, for example, fix the output, okay? In that case, the output is equal to 1, and look at the states. The probability is 0.1, 0.5. You see that the summation of these two values is not equal to 1. It really doesn't have to, because a likelihood is a distribution with respect to yk. It is not a distribution with respect to xk in general. Okay? So here let me look at an example. In the first case, case 1, let us say yk is equal to, I will here let yk take the values 1 and 2. And let us say that xk is also in 1 and 2. Okay? So in this case, I can just show this procedure like this. This is my possible y case, and this is my possible x case. All right? So xk can take the values 1 and 2, and yk can take values 1 and 2. When the number of different output values is equal to the number of different states, there is a special case of probabilities where we can model perfect information case. Okay? The perfect information case can be the probability that when xk is equal to 1, the output is equal to 1, the output is equal to 1 with probability 1, and the output cannot be equal to 2. So the output is going to be equal to 2 with probability 0. Okay? And we really do not show the probability 0 case. And if the output, when the state is equal to 2, if the output is equal to with probability 1, this is the perfect information case. This is the case when yk is equal to xk, okay? But we know that in this case we are not really interested in this. We are considering only the partial information case in these coming lectures. So let me say that the following probabilities are given to us. So let me say that this probability is given as 0.2, and let me say that this probability is given as 0.8. Okay? In this case, this is actually sufficient to know all of the other probabilities. Okay? So let me show the other probability with red color. So in this case, the second probability is given as 0.8. Sorry, my example says that this is 0.4. So remember, these two do not have to sum to 1. So here we are given these two probabilities. What are these? These are the probability that yk is equal to 1 given xk is equal to 1. And this is given as 0.2, and probability that yk is equal to 1 given xk is equal to 2, this is given as 0.4. Okay? Now from this information I can find the other two probabilities as well. Okay? So I know that probability yk is equal to 2, xk is equal to 1 is going to be 1 minus this probability, 0.8, and probability that yk is equal to 2, xk is equal to 2, that is going to be 1 minus this probability, which is 0.6. All right? In this case, usually we can show the likelihood as follows. Probability that yk is equal to 1 given xk. In this case, I write this likelihood as we are going to use this in the estimation. In the estimation, either yk is going to be equal to 1 or yk is going to be equal to 2 at any time. Okay? That is why I need to always fix the argument of this function, and I need to think about different x's here. Okay? That is what we are going to use in our measurement update. So remember, here yk is always fixed. We are measuring it, and we are considering the likelihood as a function of different xk when yk is fixed. Then we are multiplying the likelihood as a function of xk with the predicted distribution. Okay? So I can actually write this as a function of xk as follows. So I have here the case xk is equal to 1, xk is equal to 2. This is the likelihood when we fix the argument and consider it as a function of xk. This is equal to, when xk is equal to 1, this is 0.2. And when xk is equal to 2, this is, sorry, I have, when xk is equal to 2, this is 0.4. So you see that the likelihood as a function of xk is not a proper probability distribution, because when we sum these two values, we don't get 1. Okay? That is actually an example of a case when the likelihood is integrated with respect to conditioning. It doesn't have to be equal to 1. The result doesn't have to be equal to 1. And the second likelihood for the second value of the measurement, when yk is equal to 2, if I consider this probability as a function of xk, then I will write a similar thing. So here xk is equal to 1 and xk is equal to 2. And here there will be probabilities. And in this case, we have 0.8 and 0.6. And you see that we really do not have 1 when we sum these values. Then what are these likelihoods are saying to us? They are saying that when y is equal to 1, this likelihood gives it thinks that the xk is equal to 1 has a larger probability. Okay, these are not so these in this case, when I consider this with respect to xk, I cannot call these probabilities, but this, like, I have to say something like this: when yk is equal to 1, the likelihood tells us that xk being equal to 2, the event xk being equal to 2 is more likely. Okay, I shouldn't use probability here. Maybe likelihood is related to likeliness, not probableness or something like that. Okay, so here we see that the likelihood of xk being equal to 2 is larger than the likelihood of xk being equal to 1. So we have the reverse situation for the second measurement. Okay, so the question is, how do we combine this type of information? Suppose that at time k is equal to 0, y is equal to 1. At time k is equal to 2, y is again 1. At time k equals to 3, let us say that the output in that case is equal to 2. So how to combine these type of likelihoods? The answer is at the Bayesian recursion. Okay? So this was an example of case 1, where the output takes a finitely many different values. And now I can exemplify case 2. So as an example of case 2, I will take a Gaussian likelihood function. In this case, let me say that yk is a real number. State is discrete, but the output is continuous. Okay? And let us say that the likelihood pyk given xk is equal to normal yk. I have 2xk and variance 1. Okay? In this case, what do we have? In this case, our state space xk. So let me say that state space xk is discrete. So state can take only the values, and let us say xk is equal to in 1 and 2. All right? In finite state Markov chains, of course, state is always discrete. It takes finitely many number of elements. But the output can be continuous. So these are the two values that the state can take. Okay? And here, I will also show the distribution of yk. All right? If state is equal to 1, then pyk given xk is equal to 1, I have the following distribution. Normal, yk, mean is 2, because 2 times 1, and I have the variance is 1. Okay? So when the state is equal to 1, the output distribution has mean 2 and variance 1. That means that for the first state, the output is distributed like this. Okay? It is a Gaussian. Sorry for my terrible drawing. So it is a Gaussian. For the first state, when the state is at the first state, the output is going to be distributed around to value 2 with variance 1. Okay? For the second state, pyk xk is equal to 2, substitute xk equals to 2 here, then we would have the output is going to be distributed with mean 4 and variance 1 again. All right? And in that case, I will have the mean 4 here, and the output for the second state is going to be distributed with a Gaussian like this. It can take, of course, any number of values, any values here in this region here, in this support, and which value is it going to take is going to be random, which is distributed with this distribution, Gaussian distribution. Okay? So now let us say that at time k, let me say that we measured the output 0.4. Okay? I am going to change this a little bit. Let me say that we measure the output, let me say 2.1. Okay? At time k, let us say we measure this output. In that case, what I need to do is I need to specify the y component, the argument of the likelihood at 2.1, and then I look at this as a function of xk. Okay? And this is going to be equal to, when xk is equal to 1, this is going to have a value. And when xk is equal to 2, this is going to have another value. And output is always fixed here. All right? When I fix this, then I'm going to obtain the following values. This is the case when xk is equal to 1. So this is going to be normal. The evaluation of this normal distribution at point 2.1. 2.1, which means 2. And variance 1, and this is the second case is going to be normal and evaluated at 2.1 again, the mean 4 and the variance 1. Okay, so that is my likelihood function in that case. I fix the argument of the likelihood at the collected measurement, which is 2.1. And then I look at the different possible states. I look at the likelihood as a function of xk. And in this case, I can actually quite easily show that these two values are going to be somewhere here. So that is 2.1. So the second value is this number here, and the first value is this number. Okay? And these two numbers do not have to sum to 1. Okay? So now we are actually ready to go into our estimation problem. So remember, we have two quantities, the estimated PDF and the estimated and the predicted PDF. Okay? In this case, I know that the state takes only finitely many number of elements. Okay? That means that I can keep these densities in a vector with size I, just like the quantity P0 or pk that we have calculated in the past. So I'm defining here pk given k vector. Okay? In this case, this is going to be composed of some real elements, probability elements, pk given k1, pk given k2, going until pk given ki. Okay? This is going to be my estimated state distribution in a vector. Or I can say here, instead of distribution, I can say probability mass function for the discrete random variable xk. But in this case, these probabilities are not unconditional probabilities. They are conditional probabilities. And if I define pk given ki, then this is going to be probability that xk is equal to I, given all of the current and the past measurements. Okay? Now we have conditional probabilities here. And similarly, I can define the predicted distribution, k plus 1, k. This is again a horizontal vector, pk plus 1 given k1, going until pk plus 1 given ki. And when I define the elements, I get pk plus 1 given ki is defined as probability. In this case, this is probability that xk plus 1 is equal to I, given all of the current and the past measurements. Okay? So these are the vectors that we have to recursively calculate in order to be able to estimate the posterior distribution of the state. Okay? Of course, here when you look at, so the output terms are going to be given to us. We will always measure the outputs, and we're going to calculate these probabilities. So here we see something important. This probability, when I try to sum this with respect to the argument here, argument I need to get 1. Okay? So that means that when I sum these quantities, pk given ki, then I need to get 1. That means that pk given k vector times the vector 1, which is a vector which is formed of all elements equal to 1, this multiplication is going to give me scalar 1. Okay? Similarly, I have pk plus 1 given k vector times the vertical vector 1 should be equal to scalar 1. Okay? So now let us start Bayesian estimation. The initialization is simple, okay? The initialization tells us that, so I have initialization. This is simple because in this case, I will just equate the vector P0 given minus 1 to the initial state distribution. This is given to us in the definition of the Markov chain. That means that is nothing but the P0 vector. Okay? So this is the initialization of our recursion. We are going to start P0 given minus 1 with the initial distribution of the Markov chain. Because minus 1, there are no measurements called minus 1. So that means that this means no measurements, and the distribution of P0 should be P0. Okay? Let us now go into the measurement update. In this case, suppose that we have pk given k minus 1x. We have it for k is equal to 0. And we need to calculate pk given k vector. We need to start with the predicted distribution, the predicted vector, and then we need to calculate the updated vector here, okay, or the estimated vector. So here is what I'm going to do. I'm going to write the equivalent version of this one, okay. So I will set pk given k. So let me write this as follows. I know that pk given k for the case of a Markov chain is this. Xk is equal to I given y0k. Okay? That is equal to the likelihood P of yk given xk is equal to I, and pk given k minus 1 xk is nothing but the probability xk is equal to I given y0 k minus 1 divided by, I will write the same thing as the numerator. So I would have here pyk given xk is equal to I and pxk is equal to I. I'm writing the same thing here. I have 0 k minus 1, and this integral is with respect to all of the state values. I'm integrating over the whole state space. In the discrete case, this summation is going to turn into, this integral is going to turn into a summation. Okay? So I would have here a summation over the whole state space, I from 0 to capital I. Okay? This is the prediction, so this is the update or the measurement update formula for the finite state Markov chains. Now I can try to, and this is true for all I from 1 to capital I. Okay? So you see that I'm multiplying the likelihood value with the predicted distribution value, and then I'm normalizing those values here. So here let me write the equivalent versions of these quantities. This probability is nothing but the ith element of the pk given k vector. So this is pk given ki, that is equal to, this is the likelihood it's going to remain as it is, yk given, of course yk is going to be known, and we are going to consider different values of I here. Xk is equal to I. And this is my predicted distribution formula. Okay? So I would have here, in this case, pk given k minus 1, ith element. Okay? Divided by summation of these elements. I from 0 to I. Sometimes, in order to not confuse this I with the summation argument here, sometimes we do the sum with respect to another variable, like j. Okay? Here, I ask you not to confuse this index of the summation with this I here. So I would have here pyk given xk is equal to I, pk given k minus 1 I. Okay? So now let us try to first, and this is true for I equals to 1 going until capital I. Okay? So now I would like to write this operation in terms of vectors and matrices, just as we did in the case of finite state Markov chains when we first started with that topic. Okay? So now this is a vector, and you see that I want to multiply, so I have pk given k minus 1 I. This is a vector, and I have pk given k minus 1, 1, pk given k minus 1, 2, going until pk given k minus 1 I. I need to multiply each element of this vector with the corresponding likelihood. Yk is fixed, and I need to multiply the first element with the likelihood of first state, xk is equal to 1, the second element with the likelihood of the second state, etc. Okay? How can I multiply each element of a vector with a different number? So these yk, xk is equal to I, there are I numbers there. And I need to, in sequence, I need to multiply those numbers with each of the elements here. Okay? Of course, I can define a single horizontal vector for this likelihood, and I can do element-wise multiplication. But we know that element-wise multiplication is really, that is called Hadamard product, by the way, and it is sometimes used, but the book that we use really is not using it, and here I really do not want to use a Hadamard product. I do not want to define the element-wise multiplication of vectors here. Instead, I would like to apply such an operation, element-wise multiplication, with a matrix vector product. Okay? So suppose that you have a diagonal matrix, alpha 1, alpha 2, going until alpha n. Okay? And suppose that you have a vector, beta 1, beta 2, going until beta n. If you multiply this diagonal matrix with such a vector, what it is going to do is that it's going to multiply the first element with the first diagonal element, alpha 1, beta 1. And the second element is going to be alpha 2 times beta 2, going until alpha n times beta n. Okay? So multiplication of a matrix. Suppose that this is a matrix. This can be a matrix with these row vectors here. So a multiplication with a diagonal matrix from the left of a matrix would weight the rows of that matrix with the diagonal elements here. Okay? Similarly, if you have a horizontal vector, beta 1, beta 2, going until beta n, or a matrix with these columns, okay? If you multiply a horizontal vector or a matrix with these columns with a diagonal matrix from the right, alpha 1, alpha 2, going until alpha n, then you actually weight the columns of this matrix with these diagonal elements. Okay? So in that case, you get alpha 1, beta 1, alpha 2, beta 2, going until alpha n, beta n. This is what we're going to use here, because we have a horizontal vector, and we would like to weight the elements of that vector with some scalars. And that is why I am going to define a diagonal matrix which is going to contain these likelihoods in its diagonal elements. Okay? And then I will multiply that matrix with this horizontal vector, and I will multiply this horizontal vector with that diagonal matrix from the right. And then that is going to do the weighting automatically. Okay? So the first thing that I'm going to do is to define a matrix capital L. L stands for a likelihood here. The likelihood of YK matrix is going to be defined as PYK, whatever the value of the output is, XK is equal to 1, PYK, XK is equal to 2, going until PYK given XK is equal to capital I. So I look at the likelihood function, fixing the argument at the output we measure, and then I'm looking at the likelihood function as a function of different xk's. And I fill those values into the diagonal elements of a matrix, and I would put 0 everywhere else. Okay? And then I'm just going to do the following. This numerator is nothing but the first element of this vector times this diagonal element, second element of this vector times this diagonal element, and so on. Okay? So here, as a result, I can write pk given k vector as this vector, pk given k minus 1, times the likelihood matrix, L of yk, the diagonal matrix. And I know that when I multiply this vector with this diagonal matrix, I know that the elements of this vector are going to be weighted with the diagonal elements, just like this. If this was a matrix, then the columns of the matrix here would be weighted by the diagonal elements. So this is just the numerator. Numerator is just going to be a vector. And what about the denominator? Denominator is a scalar here. Okay? So it really doesn't depend on I, this index. They are different. So index of the summation is different than this. So the denominator is just a normalization constant. Okay? So what do I have to do? I have to look at the elements of this multiplication. Okay? Elements of this multiplication. I need to sum all of them, and then I need to divide this vector with that sum. Okay? How can I sum the elements of a horizontal vector? It is just an inner product operation. Okay? If I want to sum elements of a vector, I just multiply that vector with a vertical vector 1. Okay? So what I do here is nothing but this. Pk given k minus 1, I take the same vector, Lyk, and then I multiply it with a vertical vector 1. Okay? So this is our measurement update formula for the finite state Markov chains. We will take Pk given k minus 1 vector, we will multiply it with the diagonal likelihood matrix, and then we will normalize. And this normalization, this denominator is just going to give you a scalar. Why is that? Pk given k minus 1 is a vector, L is a matrix, and 1 is a vector with vertical vector with elements 1. Okay? So this is just going to be the normalization constant here. So here I can actually write this L of yk. Whatever yk is, this matrix is going to be a diagonal matrix which is formed out of the elements pyk, xk is equal to 1, pyk, xk is equal to 2, going until pyk given xk is equal to I. Okay? You have to be careful here. We are not forming this matrix for actually by using different values of y. The value of y here is fixed, whatever we measured at time k, okay? And we are changing the state values here, all right? That is L of yk. So we complete, in this case, our measurement update. So now let us go into time update. We initialized, and then we learned how to apply measurement update by using the Bayesian recursion. And then now we are ready for time update. In this case, I will of course use the prediction formula for the densities. So let me first write what those densities are. This is P. So in a finite state Markov chain, the density is going to be a probability mass function. So I would have xk plus 1 is equal to I given k, y0 to k. This is equal to, this integral is going to turn into a summation, okay? In this case, I will just write this. Instead of I will write here just j, and I will sum with respect to I, okay? So I now xk plus 1 is equal to j, yk. This is the jth element of the pk plus 1k vector. Okay, for the finite state Markov chain. And our integral turns into a summation, and then I would have a summation with respect to integral with respect to xk. That means that I would have a summation with respect to different values of xk here. Okay? So this transition distribution is going to turn into a probability, and xk plus 1 is equal to j, given xk is equal to I, summation is with respect to I, with respect to xk value, and I would have uk, okay, times the pk given k xk, and this is going to be another probability, pxk is equal to I, given y0k, okay. So this is the prediction update or time update formula for finite state Markov chains. And now I'm going to write this again using vectors. The first thing that I'm going to do is to replace this one, for example, with the corresponding vector element. This is pk plus 1 given k vector, and its jth element, okay? That is equal to, this is summation, I from 1 to capital I. What is this? By the way, there is a mistake here. This is xk plus 1 is equal to j, all right? And what is then this transition distribution? This is the element of the transition probability matrix of the Markov chain when UK is given to us. There might be different input values, and for each different input value, we have another probability transition matrix. Okay? And in that case, this is going to be the ijth element of the transition probability matrix, and I know that these elements are dependent on input value. So that is why I'm going to write this ijth element of the TPM, and this is for the input UK. Okay? And this is going to be the vector pk given k and its ith element. Okay? So I would have this. And this has to be true for j is equal to 1 to I. Now I'm going to substitute j is equal to 1, put it into the first element, substitute j is equal to 2, put it into the second element, substitute j equals to I, put it into the last element. That's going to give you the vector pk plus 1 given k. Okay? This vector is this type of summation. We have seen this type of summation in the past. When we try to update the Markov chain state probability distribution, we have seen this type of multiplication, and this actually is nothing but the multiplication of the vector pk given k with the transition probability matrix capital P for the input UK. Okay? So this is how prediction update is made for a finite state Markov chain. In the past, remember, we have actually derived such a formula. Okay? But in that case, we could predict the Markov chain without any measurements. Okay? In this case, after making such an update, we need to update the Markov chain probabilities with some measurements and then apply this update once more. This is just a single time step prediction update, and if I would like to apply prediction without any measurements, then I would continue multiplying this with the different probability transition matrices for the corresponding inputs here. Okay? But this is just a one-step prediction update with the given input here. So now we have finished the prediction update and the measurement update. Let us summarize. Initialization is P0 given minus 1 is equal to P0. The measurement update is Pk given K is equal to Pk given K minus 1 times the likelihood matrix, diagonal likelihood matrix, divided by summation of these elements, Pk given K minus 1, Lyk times the vector 1. And prediction is Pk plus 1 given K is equal to, I would have just Pk given K times P of UK. Okay? Sometimes people combine these two updates and they would get Pk plus 1 given K, Pk plus 1 given K plus 1 from Pk given K. Okay? Sometimes they do it like this. If I continue one more step here with the prediction, with the measurement update, then Pk plus 1 given K plus 1 is going to be Pk plus 1 given K times likelihood of K plus first output, okay, divided by Pk plus 1 given K, Lyk plus 1, and times 1. Okay? Then I can actually write Pk plus 1 given K plus 1 in terms of Pk only. And that is not really difficult. So it would be just Pk plus 1 given K plus 1 is equal to, instead of Pk plus 1 given K, substitute this formula. Okay? So I would have Pk given K P of UK, and I have L of YK plus 1, divided by the same thing times the vector 1. Times the vector 1. Okay? So in this case, I get a recursion without considering the predicted distributions. I get a recursion, a direct recursion between the estimated state distributions, posterior state distributions, and it is given by such a formula. So in this case, I will just consider, so here, what we did is that we obtained the posterior state distribution. We obtained Pk given K. So this is going to tell us the probabilities that the state is equal to 1, given all of the measurements, probability that state is equal to 2, given all of the measurements, and probability that state is equal to I, given all of the measurements. Okay? So this is going to give us probabilities. Given these probabilities, how can I estimate the actual value of the state? So how can I know what the state is? How can I make a guess, or what would be possible, a possible value of the state? In this case, usually in Markov chains, people would calculate a state estimate. This estimate is called xk given k I hat, okay? And this is usually found as the state that would have the maximum probability in the posterior distribution, okay? This would be xk given k is going to be the arg max I, p k given k I, okay? I choose the state which has the maximum posterior probability. Okay? And this type of estimate in estimation theory literature is called maximum a posteriori or map estimate of the state. Okay? So after calculating these probabilities, for each time, I can actually make a state prediction by calculating the maximum, the state with the maximum posterior probability. So now this brings us to the example that I'm going to solve. In this case, our Markov chain is given to us with two states, 1 and 2, and the initial state probability is 0.5, 0.5. Really, initial state probability is, states are initially probable, so we don't know which state we have as x0. And I don't consider any input, no input. If we have input, then in the prediction step, you need to consider that input at time k. In this case, I don't consider any input in my Markov chain. So in that case, the probability transition probability matrix TPM is not going to depend on the input. So I would have just a constant matrix whose elements is not dependent on the input value here. And I would say, let us say that the output takes two values, A and B. Now, instead of 1 and 2, I use the values A and B, and we are given the likelihood values. If yk is equal to A, given xk is equal to 1, and yk is equal to A, xk is equal to 2. These probabilities are 0.7 and 0.4. And we have run this system, and we have collected a specific sequence of outputs. Remember, we don't know what the state is, because we can only see the output of the system, which is probabilistically dependent on the state. Okay? So if I'm given the output A, I really don't know if the state is 1 and 2. The only thing that I can do is to calculate some posterior probabilities given those measurements. So let me say that y0 is equal to A and y1 is equal to B. Y1 is equal to A. These are the measurement sequence. This is the measurement sequence that we collect for this specific instance. Y2 is equal to B. Okay? So then the question is, find P2 given 2 state distribution. Okay? So the first thing that I'm going to do is to calculate the likelihood matrices for the different output values. So I have, let us say, L of yk is equal to A. So I will call this as L of A, the likelihood matrix. This is going to be formed of elements, probability that yk is equal to A, given xk is equal to 1, probability that yk is equal to A, given xk is equal to 2. Remember, the output is fixed, the argument is fixed, and we are looking at the likelihood function as a function of xk. So we have different xk values on the main diagonal. These are 0. So here let us look at this. So yk is equal to A is given to us, when state is 1, is given to us as 0.7. And the other probability is 0.4. See that these are not summing to 1. Okay? And L of B, this is going to be the same matrix except yk is going to be B. Okay? But I'm not given those probabilities as you see, but we know that since yk takes two values, probability that yk is equal to b given xk is equal to 1 is going to be 1 minus this probability. So which is 0.3, and 1 minus this probability is 0.6. Okay? So this is the second likelihood matrix. So now let us start our initial distribution. P0 given minus 1 vector is going to be the initial state vector, which is P0, and that is 0.5, 0.5. Actually, this distribution is a uniform distribution. Use uniform probability mass function. It maximizes the entropy. So we really don't know anything about the initial state. This is called prior information. We really don't have any prior information about the state whatsoever. But then we collect a measurement. We get our first measurement, and that is y0 equals to A. We get this measurement, and then we are asked, what is the posterior probability distribution of the state given this y0? Okay? That is going to be P0 given 0. Okay? My measurement, this is going to be a measurement update, and that is going to be P0 given minus 1 times the likelihood of the measurement A. Okay, y0 is equal to A. If I collect the measurement B, then this would be L of B. Okay, divided by P0 given minus 1, L of A times the vector 1. Okay. So that is equal to, so I have here 0.5, 0.5 times L of A is this matrix, 0.7, 0.4, 0, 0, divided by, sorry, I would have to write this again, and 1, 1. Okay? So really here, we have expressed this operation as the matrix vector multiplication, but really here you do not have to make a matrix vector multiplication. You can just multiply this 0.7 with this 0.5 and 0.4 with 0.5, okay? And that is going to give me 0.35, 0.2, okay? Divided by, so I know that this operation is nothing but summing the elements of this vector. Okay? We need to normalize this numerator so that it's a valid probability distribution. It's a valid probability mass function. Okay? So really I do not have to apply this type of multiplication here. Okay? So all I have to do is to sum these elements. It's going to be 0.55. And if you calculate this is approximately equal to 0.64 and 0.36. So these two values should always sum up to 1, because this vector is a probability mass function, is representing a valid probability mass function. That means that this element, sum of the elements of this vector should always be equal to 1. If it is not 1, then that means you have made a mistake somewhere. So what does it say to us? The posterior distribution, as soon as we collect this measurement, y0 is equal to a, the posterior probability that x0 being equal to 1 is 0.64 and x0 being equal to 2 is 0.36. Obviously, if someone asks me to guess what is the state x0, then I would calculate the estimate. x0 given 0 estimate would be the state 1. Okay? If someone asks me to calculate a point estimate, which this one is, then I would say that the estimate is x0 given 0 is 1. All right? By the way, here there is no I, of course. I'm really writing stupid things here. xk given k is, this I is which was the maximization variable, and when I do the maximization with respect to I, there is no I here. Okay? So x hat 0 given 0 is going to be equal to 1 because it has the maximum posterior probability. Okay? And then let me calculate P1 given 0. So I won't change the measurement, I won't change the given information. We still have this measurement in the given condition, but I would like to predict the next state. What can be the next state? Okay? So in that case, P1 given 0 is the prediction formula. P0 given 0 times the transition probability matrix, P. If there is an input here, if there was an input, then I would also have measured, I would also have known that that input, and then I would use the transition probability matrix corresponding to that input here. But in this case, there is no input in our system. It transitions without any inputs. So I have a fixed transition probability matrix. And that is going to be, I have 0.64, 0.36 times the transition probability matrix, 0.1, 0.9, 0.5, 0.5. Okay? If you do this multiplication, you are going to get 0.24, 0.76. This is why I will allow you to use a calculator in the exam. Okay? So here I have these posterior probabilities. This is the probability that state 1, x1 is going to be equal to 1, x1 is going to be equal to 2, given the measurement y0 is equal to a. Okay? And in this case, if I ask you, given the measurement y0, what is your estimate of the state x1? In that case, I would say that x hat 1 given 0 maximize this probability distribution, and it's going to be 2. So the first estimate of x0 turned out to be equal to 1. Estimate of x1, given the same information, turned out to be 2. Why is that? Because this transition, if the state is 1, it tells you that if the state is 1, with a very high probability, the state is going to go to 2. So if you're estimating the state x0 equal to 1, then most probably you're going to go into the second state in the next time step. Okay? And let me calculate here P1 given 1. Now we get another measurement, okay? We get the second measurement, Y1 is equal to A. We again measured the output A, and now given these two measurements, what is the probability distribution of the state, okay? Then this is going to be, I have P1 given 0, that distribution, times the likelihood matrix of A, times P1 given 0, likelihood matrix of A, times the vector 1. Okay? Now if I would like to write this, it is 0.24, 0.76, likelihood matrix of the measurement A, 0.7, 0.4, divided by the same thing times the vector 1. Okay? And that is going to be, if you do this multiplication, then you're going to end up with 0.17 times 0.30 divided by, you really do not have to make the multiplication in the denominator. You just sum these elements and divide by that number, 0.47. And this turns out to be 0.36, 0.64. So you see that I get the measurement A again, and the likelihood of the measurement A actually says that the state 1 is more likely. Okay? State 1 is more likely. And you know, you can compare how likely the states are. So we see that our prediction tells us this state distribution, and we measured a new measurement, we collected a new measurement, and now we updated the posterior distribution. You see that although the state 1 is more likely according to that measurement, in the overall here we see that the state 2 is still more probable. Why is that? Because the initial distribution is like this. Okay? So you see that a likelihood cannot really beat the prior distribution or predicted distribution immediately. Okay? So of course I know that if I continue to measure y2 is equal to a, y3 is equal to a, y4 is equal to a, etc., then the likelihood is going to converge to the normalized version. Then the PDF or PMF is going to converge to the normalized version of this likelihood. But here you see that we combined this information with the information coming from the measurement, and this is the fused information here. Okay? So we see that the new coming information cannot really overcome the prior information immediately. It needs to really take some time according to our probability calculations. So now let us predict P2. So P2 given 1 is P1 given 1 times the transition probability matrix, and this is going to be 0.36 and 0.64 times the TPM. 0.1, 0.9, 0.5, 0.5. Okay? And this is going to turn out to be approximately 0.36, 0.64. So we see that prediction will not change the state vector here. Okay? So it will not change the state distribution. Why can this be? We know that this happens if this vector is actually the left eigenvector corresponding to the eigenvalue 1 of this TPM. Okay? Well, this really doesn't change. So time propagation doesn't change anything if the state distribution is like this. This is because this vector is very close to the stationary vector or steady state distribution of this Markov chain or of this TPM. Okay? And in this case, we see no change. The prediction did not cause any increase in the uncertainty. The uncertainty remained almost exactly the same. And finally, we collect the measurement y2 is equal to, y2 is equal to b. Okay? We collected this measurement, and now we're required to calculate P2 given 2. We already have P2 given 1. P2 given 2, this is just a measurement update. P2 given 1 times the likelihood matrix of the measurement B divided by P2 given 1, LB times 1. Okay? P2 given 1 is given there, 0.36, 0.64 times the likelihood matrix 0.3, 0.600 divided by the same things times the vector 1. Okay? And if you do this multiplication, you're going to get 0.11, 0.38, and the denominator is going to be 0.49. And you would get at the end 0.22, 0.78. This is the vector posterior state distribution given all of the measurements so far. If someone asked me to calculate a point estimate for the state, I would say that x2 given 2 hat, this is the map estimate, maximum a posterior estimate, and that is going to be equal to 2, because state 2 takes the maximum probability. Okay? So this completes our investigation of finite state Markov chain estimation, or Bayesian estimation. And the next topic in the course is going to be, I'm actually going slower than I guessed. So the next topic, which is going to remain for the next week, is going to be estimation for linear Gaussian systems, which is going to be the Kalman filter. And then we're going to see properties of the Kalman filter, and that is going to take the next week, I think. If I go as slowly as I have done in this week, then it's going to take the next week. And as a result, the control with the partial information is going to remain for the last week of the course. I hope I can actually finish it. But that's all for this lecture. Thank you very much for watching. Bye.